So my project involves indoor localization with online sequential extreme learning machines, which I've implemented in Spark, as well as Spark streaming. So what's indoor localization? As the name implies, you're just trying to find the location of a device, a user, within an indoor space. So of course, outdoors, you'll be able to use GPS, and that's fine. When you're indoors, there's lots of interference with GPS signals. So you need to find different ways to handle that. So some solutions include using Bluetooth beacons, where you're just taking a Bluetooth device, placing them all around a building, and then from there you can triangulate your location, kind of like how GPS works. There's another solution called dead reckoning, where you're using something on board of your device. So like an accelerometer, understanding the velocity from the accelerometer. And from there you can estimate where the device is going. And another solution is fingerprinting, which is what we're going to be looking at here. So fingerprinting uses the ambient radio signals around you and around the device to try to triangulate where you actually are. So as you move throughout this building, you'll see different Wi-Fi access points. And by finding the different Wi-Fi access points throughout different hallways or throughout different rooms and floors, you'll be able to kind of find a fingerprint of where you are and be able to estimate where you are from that. Of course, the signal strength from those Wi-Fi access points fluctuate quite a bit. They change with the population, if there's more people or fewer people in a room, or if the environment changes, opening or closing doors. So the system would need to be able to update over time. So there's lots of work related to this, looking at different learning systems where you'll collect your data, you'll stand in one spot, collect some ambient radio, and then move to a new spot, collect more ambient radio. But the issue with these systems is you have to collect all this data in batch initially. So instead, we need some sort of online system where we can keep learning and keep understanding how the radio signals change throughout time, depending on the environment. So there's been lots of work with different models. Specifically, there's a group in Singapore who has looked at indoor localization with online sequential extreme learning machines, which we'll talk about what those are in a bit. But their implementation is in Matlab. So we're going to explore how an implementation in Spark might work. Well, okay. So the goals of the project are to look at extreme learning machines and online sequential extreme learning machines, see how those work. There's a lot of question on whether extreme learning machines are actually a good idea or if they're kind of stealing a bit too much from other sources. We won't talk about, why is it going forward? We won't talk about that too much. But also, in addition to that, we're seeing how it performs with simulations for the extreme learning machines. So what is an extreme learning machine? Extreme learning machine is a single hidden layer feed-forward network. So if you imagine an artificial neural network, that's what an extreme learning machine is. It's the same exact thing. There's small differences in how you train, but they're similar to whatever you would think of as a neural network. So you'll have some, you can't see my mouse, can you now? Wait. Oh, you can. So you have some function that takes an x, so some input x, which would be the vector of the radio signals around you. And then from that, you would get output of some value t, which would be our target value. So in our case, would be the xy coordinates for where you're located within the building. So there's some internal mathematics that we don't have to worry about too much, but the most important part about extreme learning machines is there's a few variables here. So of course, f of x, you're inputting x, which is here. There's also some function g, we don't have to worry about it. It can be a sigmoidal or hyperbolic tangent function, it doesn't matter too much. But there are variables that we haven't defined yet. There's a beta, an a, and a b, which is the bias. And the key feature here is with no, I'm good, thank you. With a With a normal neural network, with a error-back propagation system, what you would be doing is you'd be learning both the beta values and the A values here. So with extreme learning machines instead, you would only be learning the beta values here. So we'll look at what that means here. So here's a model of a neural network as you would expect it. So we have our input here with lots of connections to our hidden layer and then connections to our output layer. So error-back propagation, with error-back propagation, what you do is you first learn the beta values, and then you learn the change in beta values. And once you learn those changes in beta values, then the next step would be learning what the A values are back here. With extreme learning machines, on the other hand, you only have to learn this one model, right? Or rather, this one layer here, the weights for this layer here. So as a result of this, you often need more hidden layer neurons, simply because when you first set up the model, you set up random values for both layers. And because you've set random values here, you're not guaranteed to have really good weights here. So there can be some issues. So if you have more hidden neurons, you'll have a better chance of getting good values. So why does it keep skipping? So sometimes you'll hit and sometimes you'll miss. So there's a lot of testing that you need to handle here. But from a parallel standpoint, if we only have to learn one layer, well, we can potentially run that all in parallel. So we can see in this graph here that on the right is the error-back propagation learning. So we learn the beta values, and then only after we've learned all the beta values can we go on to learn the A values. Extreme learning machine, again, we only learn the changes in the beta values, and once those are done, we can go on with our work. So now we'll go ahead and see what I've implemented for this. We don't go into all the learning, mathematics. Why does it do that? We won't go into the mathematics of how it works, but let's take a look at the estimators that I've created. So we've got an L model. So our L model simply extends the Sparks MLlib estimator, which in general just needs a fit method. So our fit method takes in a data set, which then returns an L model. And we can see...
Steven, are you supposed to be showing the code now?
Is it not?
No.
My mistake.
You have to exit the full screen of the presentation.
Oh, really? Okay, thank you. Okay. So, sorry. So we've got our Elm class here, which is extending our estimator, the estimator class within MLlib. And from there, we need to implement certain methods. So we have a fit method, which takes in a data set, returns an L model. Here we can see it's simply calling an internal batch learn method, which again takes data set, returns L model. So we do some manipulation to create some matrices, do some linear algebra. It's not too important for what we're looking at, but it then returns a new L model, which we then use as the predictor for our system. So before we look at how the predictor works, we can look at how our online model works. So again, it has a fit method, which takes in a data set and returns an L model. But this time, if the model has not been created yet, we just default back to running our batch learn method from our Elm model, or sorry, our Elm class. But if it has been learned, if we have learned previously, then we simply call an incremental learn, which has slightly different mathematics in it. But in the end, it takes a data set and returns a new L model, which is just the same thing. So now we'll take a look at that L model, which is, again, the predictor. So we can see we have a transform method, which takes in, again, a data set, but returns a data frame, which is the same thing. We don't have to worry about it. Basically, we're taking this data set, and we're adding a column of predictions, which we calculate from our input data through some simple simple mathematics. But that's basically it. So we need a fit method for our actual estimators, and then a transform method for our predictors. So that's a bit about what we've got there. Let's see. I've also set up a streaming version of this, but the streaming version, it's a bit confusing. It's very hard to work with, in my opinion. The streaming system, it's really hard to do testing. You would need automated testing, hopefully. But there's a question on whether there should be streaming-specific learning models, whether you should create streaming-specific learning models. So in older versions of MLlib, you do have streaming-specific models, but in the more current version, they've removed that. They still exist. You can still access the old version through the ML package, but they're not available in the MLlib package. So like I said, testing's quite some trouble. So now let's look at really quickly through some simulations. So here we've got a room, a 20 meter by 20 meter room with Wi-Fi access points in each corner, and from there we have random spots within the room that we are actually collecting the signal and then running our training and then our testing on. So let's do our experiments. So we can see on the left in blue, we've got the Matlab implementation that we were looking at from the other group in Singapore, just as a comparison. So we can see here that in the first instance, we're looking at 2,000 offline training points, and then the next step, 1,000, 1,000. We can see in each of their cases, the accuracy goes down. Well, it goes from 3 meters error to 2.5 to about 1.5 to 2 meters accuracy. Ours as well goes down. But we can see that the training time for the first instance takes a huge amount of time. And what we're finding is, because Spark handles things lazily, once you call your first fit call, it starts instantiating different things within Spark, which seems to take a long time. So there's some questions on how you can handle that. There's some things we could do, but I've just ignored it for these data points. But we can see that the accuracy is going down. And it's still a bit higher than their version, but that's because there's a lot of randomness. Potentially because there's a lot of randomness in the instantiation of a Helm model. So now let's look at a slightly larger data set. So now we're looking at first 30,000 samples. First 30,000 samples, then 2,000 and 2,000. We can see for theirs, it takes 8 seconds to train on 30,000 samples, but ours takes a little less than 4 seconds. So this is where we might be seeing more improvements as we get to bigger data. Of course, there's lots of overhead with Spark, so using it on small data sets is probably not a smart move. So as we move higher, where you can see we're actually doing better than that Matlab implementation. We can see accuracies similar again. Now let's look at even bigger data frames. So that other group in Singapore, please don't do that. They only went up to 30,000 samples in their training simulations. Here we're looking at up to 100,000 and 250,000 samples. So we can see 100,000 samples in our training system only takes 7 seconds, which again is still less than the 8 seconds it takes for their system for 30,000 samples. And also, we look at 250,000 samples. Training time takes something around 13 seconds. Great. So let's look at a plot of how long it takes to actually run our training and prediction. So blue shows the amount of time for the number of instances going from 0 to 250,000 samples, how long it takes for training in blue and predictions in orange. So blue's, it's looking okay. It goes up fairly slowly, but orange is the prediction time is going up quite fast. So this might indicate that there's an issue with my prediction code. I can't quite find what it is. It's very simple code. but theoretically, it should be doing a whole lot less than what's happening in training. So that's something I need to keep looking at. So the key contributions that I was trying to get from this was to create an ELM model, an extreme learning machine, and an online sequential extreme learning machine implementation within MLlib for Spark, which this has not been done previously. There's no instances of this. And also explore how well it works in general. Further work includes trying to review those prediction issues, seeing how Spark streaming versus a regular Spark implementation would work. Is there any benefits to using streaming or not? Also, a physical experiment would make a lot of sense if you're trying to understand where people are within a room. And that's it. Any questions?